Tonight, we're going to take a slow journey to one of the most distant worlds most people can still name from memory: Pluto. If we left in 2026, how long would it actually take us to get there? By the end of the night, you'll understand why Pluto feels close when you hear its name, why it feels far when you picture the solar system, and why the real answer becomes much heavier the moment you turn that distance into years. Pluto has a strange place in the human mind. For many people, it still feels like the last stop, the final world out there. A small, cold object waiting at the edge of everything we grew up calling the solar system. Even now, years after its reclassification, the name Pluto still carries a kind of familiarity. It sounds reachable. It sounds like something you could point at on a map of the planets and say, yes, that's far, but it still belongs to the same neighborhood. And in one sense, it does. Pluto is part of our solar system. It orbits the same sun we do. It moves through the same great darkness as Earth, Mars, Jupiter, and Neptune. It is ours, in that quiet cosmic way. But that feeling of familiarity can be misleading, because once you stop hearing the name and start counting the years, Pluto changes. It stops feeling like a distant chapter in a school book and starts feeling like a real journey, a long one, a lonely one, a journey measured less by imagination and more by patience. That is where the true scale begins to settle in. The fastest spacecraft ever sent toward Pluto was New Horizons. It launched in January of 2006, and it reached Pluto in July of 2015. That is about 9.5 years of travel just to arrive for a brief flyby. Nearly a decade moving across the solar system to reach one small world. And New Horizons was fast. Extremely fast. At launch, it became the fastest spacecraft ever sent away from Earth. Even with that speed, even with years of planning, even with one of the most carefully designed deep space missions NASA had ever flown, Pluto still demanded almost 10 years. That simple fact changes the feeling of the whole question. Because now Pluto is no longer just far. It is far enough that a mission to reach it can take a noticeable part of a human life. A child starting grade school when the spacecraft launches could be a teenager by the time it arrives. Someone beginning a career could be living in a different home, a different city, maybe even a different version of their life before the spacecraft ever reaches its target. That is the kind of distance we are dealing with. And if you enjoy calm journeys like this through space, take a moment to like the video or subscribe to the channel. It's a small thing, but it helps this channel keep reaching curious people who love to fall asleep to the scale of the universe. Now, when people hear that Pluto took about 9.5 years to reach, they often have one of two reactions. Either it sounds surprisingly short, because Pluto feels like the edge of everything, or it sounds surprisingly long, because Pluto still sounds like part of our own backyard. Both reactions tell us something important. Pluto lives in a strange middle ground between familiar and extreme. It is close enough that we have seen it with human-built machines, but it is far enough that getting there already stretches the limits of ordinary intuition. And that is only the beginning of the story. Because once you accept that Pluto can take nearly a decade to reach, the next question starts pressing in almost immediately. Where exactly is this world sitting that makes even our fastest missions spend so many years just trying to cross the distance? To answer that, we have to put Pluto in its proper place. Most of us grow up with a simple picture of the solar system. The sun in the middle. Then Mercury, Venus, Earth, Mars. Then the giant planets farther out. And somewhere at the end, Pluto, still lingering in memory as the last world on the list. The problem is that this picture is tidy, and Pluto is not tidy. It sits so far from the Sun that the ordinary scale of the solar system begins to break apart. The numbers are still easy enough to say, but they stop feeling real. Astronomers often use something called an astronomical unit, or AU, to make these distances easier to compare. 1 AU is the average distance from Earth to the Sun. That is about 93 million miles, or about 150 million kilometers. Light from the Sun, moving at 186,000 miles per second, takes a little more than 8 minutes to cross that distance and reach Earth. Even that is already enormous. If you drove a car day and night at highway speed, never stopping, it would still take well over 170 years to travel 1 astronomical unit. Earth lives at 1 astronomical unit. Mars, depending on where it is in its orbit, is about 1.5 astronomical units from the Sun on average. Jupiter is about 5.2 astronomical units. Saturn is about 9.5. Uranus is about 19.2. Neptune, the last of the 8 major planets, circles at about 30 astronomical units. Pluto's average distance is about 39 astronomical units. That means Pluto is not just far. It is almost 39 times farther from the Sun than Earth is. On average, that works out to about 3.67 billion miles, or about 5.9 billion kilometers. If Earth were 1 step from the Sun, Pluto would be nearly 39 steps away. If Earth were 1 inch from the Sun on a model, Pluto would be more than 3 feet away. And the strange thing is that even these comparisons still soften the truth a little, because Pluto does not move on a nice, nearly circular path like Earth does. Its orbit is stretched out, more oval-shaped, and tilted compared with the main plane of the planets. That means Pluto's distance changes over time. At its closest point to the Sun, called perihelion, Pluto can come in to about 29.7 astronomical units. At its farthest point, called aphelion, it goes out to about 49.3 astronomical units. For a period between 1979 and 1999, Pluto was actually closer to the Sun than Neptune was, though the two worlds were never in danger of colliding because their orbits are shaped and timed differently. Pluto is locked into a stable pattern with Neptune called a resonance. That just means their orbital periods are linked in a regular ratio that keeps them safely apart over long spans of time. And those spans are long. Pluto takes about 248 Earth years to complete 1 trip around the Sun. It was discovered in 1930 by Clyde Tombaugh at Lowell Observatory in Arizona, and it still has not finished 1 full orbit since that discovery. A full year on Pluto lasts longer than the entire history of many modern countries. That is the kind of distance we are talking about. Not just a place far away, but a place whose motion itself unfolds on the scale of centuries. Then there is Neptune. Neptune at 30 astronomical units already feels remote. It is about 2.8 billion miles from the Sun, or 4.5 billion kilometers. It is cold, dim, and deep in the outer solar system. But Pluto still lies well beyond it on average, another 9 astronomical units farther out. That extra gap matters. 9 astronomical units is not a small leftover stretch. It is about 837 million miles, or roughly 1.35 billion kilometers. That is farther than the average distance from the Sun to Saturn. So when people picture Pluto as sitting just a little beyond Neptune, they miss the scale completely. Pluto is separated from the last major planet by a distance large enough to contain another giant section of the solar system. And the sunlight changes with that distance. Light gets weaker as it spreads outward. By the time sunlight reaches Pluto, it has thinned dramatically. On average, Pluto receives only about 1/1,500th of the sunlight Earth gets. Noon on Pluto would not look like night, but it would not feel like day in any earthly sense either. The Sun would still be the brightest object in the sky, but it would look much smaller, more intense, and much less generous. It would cast shadows, but weakly. The warmth we take for granted here would be gone. That weak sunlight helps explain Pluto's extreme cold. Surface temperatures can sit around -375 degrees Fahrenheit, or about -225 degrees Celsius. At those temperatures, nitrogen can freeze onto the ground. Methane can freeze too. Water ice there is so cold and rigid that it behaves more like bedrock than like ordinary ice. This is the world New Horizons was sent to. Not a nearby outer planet. Not the last easy stop. But a small frozen world in a region where sunlight is thin. Years are centuries long, and the old familiar picture of the solar system starts to give way to something larger and stranger. And once Pluto is placed there clearly, one question becomes impossible to avoid. If it really sits almost 39 Earth-Sun distances away, then how does that raw distance turn into nearly 10 full years of travel? That is the shift we have to make now. Up to this point, Pluto can still feel like a number problem. 39 astronomical units, billions of miles, billions of kilometers. Those numbers are useful, but they still sit a little too quietly on the page. To really feel what Pluto means, the distance has to become something more human. It has to become time. Because in space, distance is only fully real once you ask how long it takes to cross it. Light gives us the first clue. Light from the Sun moves at about 186,000 miles per second, or 300,000 kilometers per second. It is so fast that if you could travel at light speed, you could circle Earth more than 7 times in a single second. That is the speed that carries sunlight across the solar system. At Earth, sunlight arrives in a little over 8 minutes. At Pluto, on average, sunlight takes about 5.5 hours to arrive. That is already a striking change. A beam of light leaving the Sun could reach Earth during a short breakfast. The same beam would not reach Pluto until much later in the day. And that is light, the fastest thing we know. So even before we talk about spacecraft, the solar system is already telling us something important. The outer worlds are far enough away that even light starts to feel delayed. And yet, spacecraft are nowhere near that fast. A spacecraft does not move at 186,000 miles per second. It moves at speeds that sound impressive in daily life and painfully small in the outer solar system. New Horizons, the mission that flew past Pluto in July of 2015, left Earth at roughly 36,000 miles per hour, or about 58,000 kilometers per hour, making it the fastest spacecraft ever launched from Earth at the time. That speed is extraordinary by human standards. A passenger jet usually cruises at around 550 miles per hour. A rifle bullet may travel around 1,700 miles per hour. New Horizons was moving tens of thousands of miles per hour, and still, Pluto took nearly 10 years. That is the scale change that matters. Once you leave Earth, even extreme speed begins to look slow. A helpful way to feel that difference is to compare space missions we already know. The Moon is about 239,000 miles from Earth, or about 384,000 kilometers. Apollo 11 took about 3 days to get there in July of 1969. Mars is much farther, and robotic missions often take around 7 to 9 months to arrive, depending on the route and the positions of the planets. Jupiter, the giant world far beyond Mars, took the Galileo spacecraft a little over 6 years to reach after its 1989 launch, though that mission followed a complex path using gravity assists. Saturn took Cassini about 7 years. Neptune took Voyager 2 about 12 years from launch in 1977 to arrival in 1989. Then comes Pluto, where even one of the fastest deep space missions ever launched still spent about 9.5 years in transit. That means Pluto belongs to a category where travel begins to shape whole chapters of time. A spacecraft launched toward Pluto is not simply going somewhere far away. It is entering a mission measured in school years, presidencies, changing technology, shifting budgets, and human lives moving forward on Earth, while the probe is still on its way. A child born when New Horizons launched in January 2006 would have been old enough to start 4th grade by the time it reached Pluto. Smartphones barely existed when that mission left Earth. Pluto was still officially called the 9th planet when Clyde Tombaugh discovered it in 1930. But by the time New Horizons arrived in 2015, it had already spent years in the category of dwarf planet. That is how long Pluto travel takes. The world changes while the spacecraft is still crossing the distance. And during most of that crossing, there is no dramatic sense of arrival. There is only motion, a steady path through darkness. The spacecraft passes the orbit of Mars, then the orbit of Jupiter, then keeps going into colder and emptier space. Day after day, month after month, year after year, it is still traveling. Pluto does not get closer in a way the human eye can feel. It gets closer in numbers, in radio tracking, in calculations, in patient waiting. This is where space is big becomes something more serious. Space is big is a phrase. Space takes years is a reality. And that reality is what turns Pluto from a distant dot into a real destination. Because once distance becomes time, the question changes. It is no longer enough to say that Pluto is billions of miles away. Now we want to know what kind of speed produces a journey that long, and what our actual spacecraft are truly capable of when the target sits that far out. To feel what a Pluto mission really asks of us, it helps to stop thinking in terms of planets for a moment and think in terms of machines. Human beings do not travel to the outer solar system with brute strength or simple courage. We do it with carefully built spacecraft, narrow launch windows, and very exact speeds. And once you look at those speeds closely, something very strange happens. They sound enormous at first. Then the scale of the solar system makes them feel small again. New Horizons is the clearest example. It launched on January 19, 2006, from Cape Canaveral in Florida, aboard an Atlas 5551 rocket, with an added third stage to give it even more speed. At launch, New Horizons became the fastest spacecraft ever sent away from Earth on a planetary mission. It left Earth traveling at about 16.2 kilometers per second relative to Earth, which is about 58,000 kilometers per hour, or roughly 36,000 miles per hour. That is an astonishing speed. At 16.2 kilometers per second, a spacecraft covers almost 1,000 kilometers in a single minute. It can travel farther than the distance from Paris to Rome, or from Chicago to New York, and then some. In one day, it can cross about 1.4 million kilometers. That sounds almost unreal. On Earth, anything moving that fast would feel beyond comprehension. Commercial airplanes usually cruise around 900 kilometers per hour. The International Space Station orbits Earth at about 28,000 kilometers per hour. New Horizons left Earth at about twice that. And still, Pluto remained almost 10 years away. That is the part the solar system keeps teaching us. Speed can be extraordinary and still be swallowed by distance. Spacecraft speeds are often measured in kilometers per second, because kilometers per hour become awkward very quickly. Once something is moving tens of thousands of kilometers every hour, engineers prefer shorter, cleaner units. So a deep space mission might be described as moving at 12 kilometers per second, or 14, or 16. Those numbers sound calm. They almost sound modest. But each one means a machine is racing through space faster than a rifle bullet, faster than any airplane, faster than almost anything human beings ever build. The trouble is that Pluto is not a target a few million kilometers away. Pluto sits billions of kilometers from the inner solar system. And when the journey is that large, even 16 kilometers every second becomes a long, patient crossing rather than a sudden arrival. This is where comparison helps. If you sent a signal made of light to Pluto, it would arrive in about 5.5 hours on average. If you sent New Horizons, even with its record-setting launch speed, you were signing up for about 9.5 years of travel. Light could make the crossing between breakfast and evening. A spacecraft needed nearly a decade. That difference tells you how slow all human spaceflight still is when measured against the size of the solar system. And New Horizons was no sluggish probe. Its speed after launch was so high that it passed the Moon's orbit in about 9 hours. Apollo missions had needed roughly 3 days to reach the Moon. New Horizons crossed that same general distance in less than half a day. It reached Jupiter in just over a year, arriving for its gravity assist on February 28, 2007. Even that trip to Jupiter, which sounds almost impossibly fast, was only the opening part of the route. After Jupiter, there were still more than 8 years left before Pluto. That detail matters because it separates human intuition from deep space reality. Many people hear that New Horizons was the fastest spacecraft ever launched toward another planet and assume the rest must have unfolded quickly. But that is not how outer solar system missions feel in practice. They feel fast at departure and slow in experience. The spacecraft leaves Earth with tremendous energy, then spends years crossing a darkness so large that even constant high speed produces only gradual progress. Other missions help show the same pattern. Voyager 2, launched in 1977, needed about 12 years to reach Neptune in 1989. Cassini, launched in 1997, took about 7 years to reach Saturn in 2004. Juno, launched in 2011, took nearly 5 years to reach Jupiter in 2016. These are not signs of weak engineering. They are signs of honest scale. The planets are that far apart. Pluto simply pushes that truth farther outward. So when we say New Horizons was one of our fastest and most capable deep space missions, we should hear both sides of that sentence at once. It was fast enough to break records, fast enough to leave the moon far behind in hours, fast enough to cross the orbit of Jupiter in about a year. And still, Pluto remained a long-duration mission, the kind that unfolds across school years and election cycles and major changes back on Earth. That is what our fastest missions actually manage. They do not erase the size of the solar system. They reveal it. And once that is clear, a more precise question begins to form. If one of our fastest planetary missions still needed about 9.5 years to reach Pluto, was that simply the normal cost of going that far? Or did New Horizons benefit from a set of unusually favorable conditions that made its trip faster than most Pluto missions could ever hope to be? That is what makes New Horizons such an important benchmark. It was not a slow mission. It was not a compromise mission limping its way toward Pluto. It was, by the standards of modern planetary exploration, a very strong shot. And that is exactly why its travel time matters so much. If a mission built that well still needed almost 10 years, then Pluto is telling us something plain and difficult about distance. It is not casually reachable. It does not sit waiting just beyond the next horizon. It sits far enough away that even one of our best modern attempts still had to spend nearly a decade getting there. New Horizons launched on January 19, 2006. It flew from Cape Canaveral Space Force Station in Florida on an Atlas 5551 rocket, the most powerful version of that rocket then available, with a Star 48B third stage added to push the spacecraft even harder. At liftoff, the stack weighed hundreds of tons, but the spacecraft itself was relatively small, about the size of a grand piano, with a launch mass of roughly 478 kilograms. That was part of the design logic. If you want high speed, it helps to keep the payload light. The mission had one clear purpose: reach Pluto as efficiently as possible, study it during a fast flyby, and send back data before continuing deeper into the Kuiper belt, the wide outer region beyond Neptune filled with icy bodies left over from the solar system's formation. The spacecraft did not slow down to inspect worlds along the way. It was not sent to orbit Pluto. It did not carry the huge fuel load that would be needed to break into orbit around such a distant target. It was built for speed and for a narrow scientific encounter. That choice matters. New Horizons was fast partly because it accepted a limited kind of arrival. It would rush through the Pluto system once, gather as much as it could, and keep going. Even with that stripped-down goal, the trip still took about 9 years, 5 months, and 25 days. From January 19, 2006 to July 14, 2015, New Horizons crossed the solar system on one of the most ambitious planetary trajectories ever flown. On July 14, 2015, it passed Pluto at a distance of about 12,500 kilometers above the surface, or roughly 7,800 miles. It raced by at around 13.8 kilometers per second, relative to Pluto, which is about 49,600 kilometers per hour, or a little over 30,800 miles per hour. At that speed, there was no second chance. The main close-up science happened during a brief window around closest approach, after nearly a decade of waiting. And that was the good version. That is the benchmark we have to hold on to. 9.5 years was not the result of a weak rocket, or poor mission planning, or a clumsy route. It was the result of a high-energy launch, a carefully designed spacecraft, and a mission plan shaped from the beginning around getting there as fast as possible. You can see that urgency in the timeline itself. New Horizons crossed the orbit of the Moon in about 9 hours. It passed Mars's orbit in just over 3 months. It reached Jupiter in a little over a year, arriving for its gravity assist on February 28, 2007. Then it spent more than 8 more years continuing outward to Pluto. That long second stretch matters because it shows how deep Pluto really is. Even after a record-setting launch and a major boost from Jupiter, the spacecraft still had most of the journey left. By the time New Horizons arrived, the world it had left behind had changed in visible ways. When it launched, YouTube was barely getting started. The first iPhone had not yet been released. Pluto had only recently been discovered to have 4 small moons beyond Charon, and 2 more would still be found later. By the time the flyby happened in 2015, children born at launch were old enough to read about the mission in school. That is the kind of time Pluto asks for even when the mission goes well. And the mission did go well. New Horizons gave us our first clear look at Pluto's bright heart-shaped plain, Sputnik Planitia, a basin filled with nitrogen ice. It revealed mountains made largely of water ice, some several kilometers high. It showed haze layers in Pluto's thin atmosphere. It transformed Pluto from a blurry point of light into a real place with weather, geology, and texture. The science return was remarkable, but the deeper lesson came before the photographs. The deeper lesson was the length of the crossing itself. A fast, focused, well-designed spacecraft, a top-tier launch vehicle, a mission plan built to minimize delay, a gravity assist from Jupiter, and still, almost 10 years. That is why New Horizons matters so much in this story. It is not just proof that Pluto can be reached. It is proof that even a very good Pluto mission still unfolds on a long human timescale. You do not reach Pluto the way you reach a nearby world. You commit to it. You wait for it. You build around it. And once that becomes clear, the natural question grows sharper. If New Horizons was this fast and still needed nearly a decade, what special advantages did it have that allowed it to perform that well at all? That 9.5-year trip did not happen because Pluto was easy to reach. It happened because almost everything about the mission was arranged in its favor. New Horizons was launched at the right time, on the right rocket, with the right kind of mission plan, and with one of the most important gifts deep space travel can receive: help from a giant planet. Without that help, the trip to Pluto would have taken longer, in some cases much longer. The most important boost came from Jupiter. After launching from Florida on January 19, 2006, New Horizons headed outward across the inner solar system and reached Jupiter on February 28, 2007. That was just over a year after launch. The spacecraft did not go there to stop and study Jupiter in the slow, patient way Galileo or Juno did. It went there mainly to steal speed. This is what a gravity assist does. A gravity assist, sometimes called a slingshot, is a maneuver where a spacecraft flies past a moving planet and uses the planet's gravity to change its path and increase its speed relative to the Sun. Jupiter is especially useful for this because it is massive. It contains more than twice the mass of all the other planets combined. It circles the Sun at about 13 kilometers per second, and a spacecraft that approaches it in the right way can leave with some of that motion added to its own solar system journey. That is what New Horizons did. When it swept past Jupiter, it came within about 2.3 million kilometers, or roughly 1.4 million miles, of the giant planet's cloud tops. That flyby increased the spacecraft's speed by about 4 kilometers per second relative to the Sun. 4 kilometers per second may sound modest beside the large launch numbers, but over a journey lasting years, that extra speed mattered enormously. It shaved several years off the trip to Pluto. A mission that might otherwise have taken roughly 12 or even 13 years was pushed down to about 9.5. That is the kind of difference Jupiter can make. And Jupiter gave the mission something else besides speed. While New Horizons was there, it also tested its instruments, observed Jupiter's atmosphere, studied the volcanic plumes of Io, and examined Jupiter's faint ring system. So the flyby was scientifically useful. But in the larger story of reaching Pluto, Jupiter was there first and foremost as a cosmic accelerator. The catch is that Jupiter cannot help whenever we want. Gravity assists depend on geometry. They depend on where Earth is, where Jupiter is, where Pluto is, and what kind of path can connect them at the right times. Planets are always moving. Earth takes 1 year to orbit the Sun. Jupiter takes about 11.86 years. Pluto takes about 248 years. That means the good launch opportunities do not repeat every few months in some easy rhythm. They open and close according to a much larger clock. For New Horizons, the best launch window was in early 2006. If the spacecraft had launched later and missed that favorable Jupiter alignment, the mission would have faced a worse trajectory. NASA planners were very aware of that. In fact, there was real concern at the time that delays could push the mission out of its preferred launch period. Missing the main window would not necessarily have cancelled the Pluto mission, but it could have added years to the flight, reduced payload options, or forced a different route altogether. This is why the famous Pluto trip cannot be treated as a standard answer. It was not simply, "This is how long Pluto takes." It was closer to, "This is how long Pluto took when the launch energy was high. The spacecraft was relatively light. The mission accepted a fast flyby instead of orbiting, and Jupiter was sitting in just the right place to help." Take away any one of those advantages, and the timeline changes. If the launch vehicle is weaker, the spacecraft leaves Earth slower. If the spacecraft is heavier, the rocket has more mass to push. If Jupiter is not in a useful position, there may be no free boost waiting in the outer solar system. If the mission is designed to orbit Pluto, rather than race past it once, then extra fuel and a more complex arrival plan must be added, which can slow the whole mission down. A Pluto mission is not one simple template. It is more like a narrow solution built around timing, mass, speed, and planetary motion all working together. That is part of what makes the outer solar system so different from ordinary travel. On Earth, if a road trip takes too long, you can often just leave earlier, drive longer, or choose a faster road. In space, the roads themselves are moving. The helpful intersections between worlds do not stay in place. A missed launch window is not like missing a bus. It is more like missing a bridge that only lines up once in many years. So New Horizons was not just fast, it was favored. Favored by a strong rocket. Favored by a light, efficient spacecraft. Favored by a flyby mission design. Favored by Jupiter's position in 2007. Favored by timing that mission planners were careful not to lose. And once timing enters the story, Pluto begins to change again. It stops looking like a distant but fixed destination and starts looking like something harder to catch. A world moving on its own long path, waiting not just for speed, but for the right moment. There is another reason a trip to Pluto refuses to stay simple. Pluto is not parked at one steady distance, waiting patiently in the same spot year after year. It is moving slowly but constantly, along a long and unusual path around the Sun. So when people ask how long it would take to reach Pluto, the question sounds cleaner than it really is. Because Pluto itself is part of the problem. The target is traveling. Pluto takes about 248 Earth years to complete one orbit of the Sun. That means Pluto has still not finished a full year since it was discovered in 1930 by Clyde Tombaugh at Lowell Observatory in Flagstaff, Arizona. A person could live a long life, grow old, and die without ever seeing Pluto complete one full trip around the Sun. That alone tells you this world belongs to a slower rhythm than the inner solar system. Earth returns to roughly the same place every 365 days. Mars does it in about 687 days. Jupiter takes about 12 years. Pluto needs almost 2.5 centuries. Its orbit is also shaped differently from the orbits of the 8 major planets. Most of the major planets follow paths that are fairly close to circles, at least by solar system standards. Pluto's path is more stretched out. Astronomers call that an elliptical orbit. Elliptical just means oval-shaped, so Pluto is sometimes much closer to the Sun and sometimes much farther away. At its closest point, called perihelion, Pluto comes in to about 29.7 astronomical units. At its farthest point, called aphelion, it reaches about 49.3 astronomical units. That is a huge difference. Using the same scale as before, 1 astronomical unit is the average distance from Earth to the Sun, about 93 million miles or 150 million kilometers. So the difference between Pluto's nearest and farthest distances from the Sun is almost 20 astronomical units. That is nearly the distance from the Sun to Uranus. In other words, Pluto does not just drift slightly inward and outward. It swings across a range so large that its own orbit contains a difference bigger than the full span from the Sun to some major planets. Its orbit is tilted too. The planets mostly travel around the Sun in roughly the same flat plane, like coins circling on a tabletop. Pluto does not stay close to that tabletop. Its orbit is tilted by about 17 degrees. That may not sound dramatic at first, but in orbital terms, it is enough to lift Pluto well above and below the main planetary plane during different parts of its journey. So Pluto is not only changing its distance from the Sun, it is also moving through a path that is slanted compared with the more orderly tracks of most planets. That makes mission geometry harder. A spacecraft leaving Earth cannot simply aim for one fixed ring in space and assume Pluto will be there. Mission planners have to calculate where Pluto will be years later, when the spacecraft finally arrives. They must account for Earth's motion, Jupiter's motion if a gravity assist is involved, Pluto's slow but steady motion, and the exact shape of the spacecraft's path through the solar system. A small change in launch timing can lead to a very different arrival geometry years later. This is one reason Pluto missions are so sensitive to timing. For part of its orbit, Pluto is closer and more favorable. For other parts, it is farther and more difficult. The slanted orbit changes the approach angle too. And because Pluto moves so slowly, the good opportunities do not refresh quickly in the way they might for a nearby target. The solar system has to be caught in the right arrangement. Pluto is also locked in a stable orbital pattern with Neptune. For every 2 times Pluto goes around the Sun, Neptune goes around 3 times. This pattern keeps the two bodies safely separated even though Pluto's orbit crosses inside Neptune's distance from the Sun for part of its journey. That stability is useful for the solar system, but it adds one more reminder that Pluto's motion is not simple or casual. It is part of a larger clockwork. So by this point, Pluto has changed again in our mind. It is no longer just a cold object almost 39 astronomical units away on average. It is a moving destination with a 248-year year, an elongated path, and a tilted orbit that changes the shape of the trip over time. And once that sinks in, the question becomes harder in a useful way. Because if Pluto is moving on a slow, awkward path of its own, then how long would it take to get there? Cannot possibly have one single universal answer. That means the question has to become more precise. How long would it take to get to Pluto? Sounds like it should have one clean answer, the way a road trip might. But Pluto travel time changes depending on what kind of mission is being flown, how much speed the launch provides, whether Jupiter is in a useful place to help, and what reach Pluto actually means in the first place. A fast flyby is one kind of mission. An orbiter is another. A lander would be harder still. New Horizons was a flyby mission. It launched in January 2006, used a Jupiter gravity assist in February 2007, and reached Pluto in July 2015. That mission was built around speed. The spacecraft was kept relatively light. It did not carry the large fuel load needed to slow down and enter orbit around Pluto. It was sent to race through the system once, gather as much science as possible during a brief close pass, and then continue outward into the Kuiper belt. That kind of mission gives you the shortest realistic Pluto timeline with today's broad level of technology. But a flyby only gives you a short look. New Horizons came within about 12,500 kilometers of Pluto's surface at closest approach. It revealed Sputnik Planitia, the wide basin of nitrogen ice shaped like the western half of Pluto's bright heart. It showed mountains made of water ice and layers of blue atmospheric haze. But the close-up part of the encounter happened in a narrow window measured in hours. After that, the spacecraft was already leaving. A flyby reaches Pluto in one sense, but it does not stay. An orbiter would be a different story. To orbit Pluto, a spacecraft would need enough fuel, or some other braking method, to slow down when it arrived. Pluto's gravity is much weaker than Earth's. Pluto's mass is only about 0.2% of Earth's mass. That means arriving fast is easy compared with stopping. If a spacecraft comes in too quickly, Pluto cannot easily grab it. It will just pass by and keep going, the way New Horizons did. So an orbiter usually means either a heavier spacecraft carrying more fuel, or a longer mission with a more complicated route, or both. More fuel adds mass. More mass usually lowers launch speed unless a bigger rocket is used. A slower departure can add years. By the time you build a mission capable of staying at Pluto, the travel profile begins to look very different from a record-setting flyby. A lander raises the difficulty again. Landing means reaching Pluto, slowing down, descending through its thin atmosphere, if that is part of the plan, and surviving contact with a surface that sits around -225 degrees Celsius, or about -375 degrees Fahrenheit. Pluto's atmosphere is mostly nitrogen, but it is extremely thin and changes with the seasons as surface ice freezes and thaws. A lander would need much more than speed. It would need power, thermal protection, guidance, and a way to operate in deep cold with sunlight about 1/1500th as strong as Earth receives. So even the phrase "reach Pluto" is doing more work than it first appears to do. If it means fly past Pluto once, the answer may be something like New Horizons. If it means orbit Pluto and study it for months or years, the answer becomes longer and more difficult. If it means land there and work on the surface, the answer stretches further still. Then there is timing. A launch window can make the difference between a faster route and a much slower one. New Horizons benefited from Jupiter being in a favorable position for a gravity assist. If Jupiter is badly placed, that boost may disappear or become less useful. Without the right planetary geometry, mission planners may have to accept a slower path, a longer cruise, or a different design altogether. So there is no single Pluto travel time sitting out there waiting to be read off a chart. There are several possible Pluto journeys, and they depend on mission type, launch energy, planetary alignment, and what kind of arrival is being attempted. And once the answer depends on all of that, the title question has to tighten. Because asking how long it would take to reach Pluto is no longer enough by itself. The more useful question becomes what leaving in 2026 would actually allow us to do. So if we left in 2026, what would really be different? Some things would be better. Our computers are far more capable than the ones that guided deep space missions in the 1970s, 1990s, or even the early 2000s. Spacecraft today can process more information on board, react more quickly to problems, and navigate with greater precision. A modern probe can carry smaller cameras with higher resolution, better star trackers for orientation, and more capable fault protection software. A star tracker is a device that looks at the sky, identifies familiar stars, and uses them like landmarks to figure out exactly where the spacecraft is pointing. New Horizons had these kinds of tools too, but a mission launched in 2026 could use newer electronics, faster processors, and more flexible onboard decision-making. That matters. It can make a spacecraft more reliable. It can help it aim instruments more precisely during a fast flyby. It can help engineers compress data better, manage power more efficiently, and recover more gracefully from small failures. But those are improvements around the edges of the larger problem. They help the mission behave better. They do not suddenly make Pluto close, because the most stubborn part of a Pluto mission still lives in propulsion, and propulsion has changed much less dramatically than computing. A spacecraft launched in 2026 would still almost certainly begin its journey on a chemical rocket. Chemical rockets are the familiar kind that burn fuel and oxidizer together, producing hot gas that rushes out the back and pushes the vehicle upward. The Saturn V that sent Apollo astronauts toward the Moon used chemical propulsion. The Atlas V that launched New Horizons used chemical propulsion. SpaceX's Falcon Heavy uses chemical propulsion. NASA's Space Launch System uses chemical propulsion. The details differ. The engines differ. The materials, software, and manufacturing have improved. But the basic idea remains the same. And chemical rockets have a built-in limitation. They can produce tremendous thrust, which is exactly what you need to leave Earth. Earth's gravity is strong, and the atmosphere adds drag during ascent. So the opening stage of any serious deep space mission still depends on brute force. You need a rocket powerful enough to lift the spacecraft, its fuel, its protective structure, and everything else off the launch pad and accelerate it to escape speed. Earth's escape velocity is about 11.2 kilometers per second, or roughly 25,000 miles per hour. That is the minimum speed needed to break free of Earth's gravity without more propulsion. But escaping Earth is only the beginning. Pluto is still out there, billions of kilometers away. And once you are in space, the launch energy you manage to build into the spacecraft matters enormously. That energy determines how quickly you begin the long outward crossing. In mission planning, this often comes down to three stubborn things: how much mass you are carrying, how powerful your launch is, and whether any giant planet can help you later. Mass always matters. A lighter spacecraft is easier to accelerate. New Horizons weighed under 500 kilograms at launch. Cassini, which was designed to orbit Saturn and carry a lander, weighed over 5,600 kilograms at launch. That heavier mission carried more equipment and more fuel, but it paid for that with a slower and longer route. Pluto missions feel this trade-off very sharply. Add more instruments, more shielding, more fuel, or landing hardware, and you usually lose some speed unless the launch system becomes far more powerful. Gravity assists matter too. If Jupiter is in a useful place, a Pluto mission can borrow speed the way New Horizons did in 2007. If Jupiter is poorly placed, the mission may lose that opportunity and face a slower direct route or a very different path through the solar system. That is why leaving in 2026 does not mean starting fresh with a blank slate. It means accepting the same broad rules that shaped Pluto mission planning before. Launch hard, keep mass under control, use planetary alignment if it helps, and accept that every gain is costly. So a 2026 departure could certainly be smarter than New Horizons. It could be guided more elegantly. It could use better electronics, better fault detection, better imaging, and better onboard autonomy. But it would still be living inside the same physical structure of the problem. The rocket still has to push real mass. The spacecraft still has to cross real distance. Pluto is still moving. Jupiter is still either helpful or unhelpful depending on the calendar. And once that becomes clear, the next conclusion starts to press forward almost on its own. If better software only improves the mission around the edges, then the deepest part of the problem must still be speed itself. That brings us to the stubborn core of the whole journey. A trip to Pluto is, above all, a speed problem. Distance matters, of course. Pluto sits billions of kilometers away. But distance by itself is only a number. What gives that number its weight is the speed of the spacecraft trying to cross it. If Pluto were 1/10 as far away, the trip would feel manageable. If our spacecraft were 10 times faster, the trip would feel different too. What makes Pluto hard is the combination: a very distant target and a machine that can only gain so much speed. The farther the destination, the more brutally travel time depends on velocity. That relationship is simple enough to say. If you double your average speed, you cut the travel time roughly in half. If you add only a little speed, you save only a little time. But when the total journey lasts many years, even a modest change can become important. A gain that sounds small on paper can save months, sometimes years. You can see that in New Horizons. At launch, New Horizons left Earth at about 16.2 kilometers per second relative to Earth. That works out to about 58,000 kilometers per hour, or roughly 36,000 miles per hour. After its Jupiter gravity assist in February 2007, it gained several more kilometers per second relative to the Sun. That extra speed helped pull the total Pluto travel time down to about 9.5 years. If that spacecraft had been significantly slower, the mission would have stretched outward. The years would pile up. The same destination would still be there, but the cost in time would keep rising. And the numbers scale quickly. At 1 kilometer per second, a spacecraft covers 86,400 kilometers in a day. At 10 kilometers per second, it covers 864,000 kilometers in a day. At 16 kilometers per second, it crosses about 1.4 million kilometers in a day. Those daily distances sound huge, and they are huge. But Pluto's average distance from the Sun is around 5.9 billion kilometers. That is why even a machine moving faster than almost anything humans have ever built can still spend nearly a decade on the way. This is also why launch energy is so valuable. In deep space mission planning, engineers care intensely about how much energy a launch can give a spacecraft at the beginning. A faster departure means the spacecraft starts eating into the distance sooner and keeps that advantage for years. A small boost at the start does not just save a little time near Earth. It keeps paying off day after day, month after month, all the way out through the solar system. That is one reason gravity assists matter so much. Jupiter gave New Horizons extra speed without requiring the spacecraft to carry extra fuel for that part of the journey. It was like finding a moving ramp in deep space and using it at exactly the right moment. That added speed translated directly into fewer years spent crossing the dark. And yet every bit of speed is expensive. A faster mission usually means a more powerful rocket, a lighter spacecraft, a more favorable launch window, or some combination of all three. Engineers do not get speed for free. They buy it with fuel, with mass limits, with narrower timing, and with harder design choices. A heavier spacecraft can carry more instruments or more shielding, but it is harder to accelerate. A lighter spacecraft can move faster, but it may have to give something up. That is why speed often decides whether a mission feels exciting or impractical. A mission that reaches Pluto in about 9 or 10 years is long, but still manageable within a scientific career. The engineers who launch it can expect to see the arrival. The students who follow it in school can grow up with the mission still active. But push that travel time much farther out, toward 15 or 20 years, and the mission begins to feel more fragile. Teams change, budgets shift, hardware ages, public attention fades. The science is still worth doing, but the human structure around the mission becomes harder to maintain. So Pluto teaches a very clear lesson. Reaching the outer solar system is not mainly about bravery, and not mainly about maps. It is about whether a spacecraft can build and keep enough speed to make the trip meaningful on human timescales. And once speed becomes the center of the story, the next question rises almost immediately. If speed matters this much, why can we not simply keep adding more of it? At first, the solution sounds easy. If Pluto takes too long to reach, then the spacecraft should simply go faster. That idea makes sense for a car, a train, or even an airplane. But rockets live under a stricter rule. Every extra bit of speed has a price, and the price usually arrives in the form of more fuel, more mass, and a harder launch. The central idea is called the rocket equation. The name sounds intimidating, but the meaning is simple. A rocket has to carry the fuel it plans to burn. That fuel has mass. So if you want the spacecraft to go faster, you usually need more propellant, which is the fuel a rocket uses for thrust. But adding more propellant makes the spacecraft heavier. And a heavier spacecraft needs more energy to speed up. That often means even more propellant. The mission starts chasing its own tail. This is why fast, deep space travel becomes expensive so quickly. Imagine trying to throw a small backpack across a field. Then imagine trying to throw the same backpack after filling it with bricks. The second throw is harder because the payload is heavier. A rocket faces the same kind of problem, except the added weight is often the fuel itself. The spacecraft is carrying the mass needed to accelerate its own mass. That is the trap. New Horizons escaped part of that trap by staying relatively light. At launch, it weighed about 478 kilograms, a little over 1,050 pounds. That is remarkably light for a mission traveling all the way to Pluto. Cassini, the mission that went to Saturn and carried the Huygens lander to Titan, launched at more than 5,600 kilograms. Cassini carried much more hardware and much more fuel, but it paid for that with a slower, longer, more complex route through the solar system. For Pluto, mass control becomes even more important because the target is so far away. A little more speed at launch can save months. A larger increase can save years. But achieving that higher speed may demand a more powerful rocket, tighter design limits, or a smaller scientific payload. Engineers do not get to ask only, how fast can we go? They also have to ask, what are we willing to leave behind in order to go that fast? That trade-off shows up everywhere. A bigger rocket can help, but bigger rockets are expensive. They take years to develop, years to schedule, and large budgets to fly. A lighter spacecraft can help too, but a lighter spacecraft may carry fewer instruments, less shielding, or less fuel for course corrections later. Even mission reliability can be pulled into the bargain. Redundant systems, which are backup components carried in case something fails, add mass. That extra mass improves safety, but it makes speed harder to buy. So faster travel often means paying in money, complexity, or scientific capability. A Pluto mission with more instruments can study more things. A faster Pluto mission may have to trim some of that scientific ambition to stay light enough for a strong launch. A spacecraft built to arrive sooner may reach Pluto with less flexibility than a slower, heavier mission, built to do more once it gets there. And the costs do not stop at launch. If a spacecraft uses its own engines for added speed, after leaving Earth, it has to carry that extra propellant the whole way until it burns it. That added mass affects the entire journey from the first second onward. Every kilogram matters. In deep space mission design, people count mass carefully enough to worry about the weight of wiring, brackets, insulation, and bolts. That level of attention tells you how unforgiving the problem is. Pluto sits far enough away that speed is precious, but speed is also heavy, expensive, and difficult to achieve. That is why just go faster is one of those ideas that sounds simple from a distance and turns complicated the moment a real spacecraft has to be built. And once that becomes clear, another pressure starts to build. Because getting to Pluto faster is only one part of the journey. A spacecraft may be able to reach Pluto quickly enough for a dramatic flyby, but arrival brings its own challenge. Speed helps you cross the distance. It also makes it harder to stop. And that changes the problem completely. A spacecraft can reach Pluto in one sense, simply by getting there fast enough to pass through the system once. That is what New Horizons did on July 14, 2015. After traveling for about 9.5 years, it rushed past Pluto at roughly 13.8 kilometers per second relative to Pluto, which is about 49,700 kilometers per hour, or a little over 30,000 miles per hour. At that speed, the spacecraft crossed the distance from New York to Los Angeles in about 4.5 minutes. That is fast enough to visit Pluto. It is not fast enough to stay. A flyby mission works because it accepts that briefness from the start. The spacecraft comes in on a carefully aimed path, gathers as much data as it can during the closest approach, takes images, measures the atmosphere, maps the surface, and then keeps going. That kind of mission treats Pluto like a target you pass, not a place you settle into. New Horizons was built for exactly that. Its sharpest images of Pluto came from a narrow window around closest approach. The most detailed science happened over hours, not weeks. The spacecraft recorded mountains made of water ice, broad nitrogen ice plains, haze layers in Pluto's thin atmosphere, and the bright basin now called Sputnik Planitia. It transformed Pluto from a blurry dot into a real world. But it did all of that while moving too fast to remain there. Once the encounter was over, New Horizons was already heading deeper into the Kuiper belt. An orbiter would face a much harsher requirement. To orbit Pluto, a spacecraft has to arrive and then lose enough speed for Pluto's gravity to capture it. That is the key word: capture. A world can only hold a spacecraft in orbit if the spacecraft is moving slowly enough for gravity to bend its path into a closed loop, instead of letting it shoot past and disappear into space. And Pluto is not a very strong captor. Pluto is only about 2,377 kilometers wide, smaller than Earth's moon, and its mass is tiny compared with the major planets. Surface gravity on Pluto is only about 6% of Earth's. A person who weighed 100 pounds on Earth would weigh about 6 pounds there. That weak gravity is part of what makes Pluto interesting, but it also means a fast incoming spacecraft gets very little help slowing down. Jupiter can grab a spacecraft dramatically because Jupiter is enormous. Pluto cannot. So if you want to orbit Pluto, the spacecraft usually has to do most of the braking itself. That means carrying extra propellant all the way from launch. And that brings the old problem back immediately. More propellant means more mass. More mass means a harder launch. A harder launch often means lower departure speed unless you use a bigger rocket or sacrifice payload. The mission starts getting heavier and slower at the same time. This is why deceleration can be just as difficult, strategically, as acceleration. A mission designer can choose a fast flyby and accept a brief encounter. Or they can aim for orbit, which asks for a different class of mission altogether. Slowing down at Pluto is not some small final adjustment near the end of the trip. It has to be paid for from the beginning, built into the rocket, the spacecraft, the fuel budget, and the timeline years before launch. The problem would become even harder for a lander. A lander would first need a spacecraft to reach Pluto, then slow enough to enter orbit, or at least control its approach, then descend toward a surface sitting around -225 degrees Celsius. Pluto's atmosphere is extremely thin, far too thin to make landing easy in the way a thick atmosphere can help slow a spacecraft. So a landing mission would need careful braking, guidance, and thermal control in one of the coldest environments any probe has ever tried to reach. All of this means arrival is not a single event. It is a choice about what kind of arrival the mission can afford. A fast flyby can reveal a world in breathtaking detail for a few hours. An orbiter can stay, circle, and watch change over time. A lander can touch the surface and work in place. Each step deeper into really reaching Pluto demands more mass, more planning, more cost, and much more patience. And once that sinks in, one conclusion becomes hard to avoid. Flying past Pluto and truly reaching Pluto are no longer the same thing. That difference is what makes Pluto so revealing. Humanity has already shown that it can cross Pluto's distance. What we have not shown is that we can arrive there gently, remain there, and work there in a controlled way for months or years. Those are two very different achievements. New Horizons proved the first one. It launched in January 2006 and reached Pluto in July 2015. At closest approach on July 14th, it passed about 12,500 kilometers above Pluto's surface. The spacecraft was moving so quickly that the entire close encounter unfolded in a narrow window. The sharpest images, the best atmospheric measurements, the closest look at Charon, Hydra, Nix, Kerberos, and Styx, all came from a brief passage through the system. Pluto went from a fuzzy point of light to a world with ice plains, layered haze, and mountains several kilometers high. The science was extraordinary, but it was also brief by design. New Horizons did not settle into orbit. It did not circle back for another look. It did not watch Pluto over changing seasons, or monitor its atmosphere month after month, or send down a lander. It came in once, fast, and left. In fact, the flyby happened so quickly that the spacecraft stored much of its science data on board, and then spent about 15 months sending that data back to Earth at a very slow rate. The close pass lasted hours. The download lasted until late October 2016. That gives you a good sense of the imbalance. Gathering the images was fast. Living with the distance was slow. That is what a flyby can do. It can reveal a world in a flash. Staying is harder. One reason is Pluto's gravity. Pluto is only about 2,377 kilometers across, and its mass is tiny compared with the major planets. It has only about 0.2% of Earth's mass. Its surface gravity is about 0.62 meters per second squared, compared with Earth's 9.8. Its escape velocity, the speed needed to get away from Pluto's gravity, is only about 1.2 kilometers per second. Earth's is 11.2 kilometers per second. Jupiter's is nearly 60. That weak gravity helps in one narrow sense. If you ever wanted to leave Pluto's surface, lifting off would be easier than lifting off from Earth. But on arrival, weak gravity is not generous. It does very little to help capture a fast incoming spacecraft. A vehicle racing in from the outer solar system can pass Pluto and Charon with almost no natural braking. Pluto simply does not have the mass to grab it the way a larger planet can. So if you want to stay, you usually have to bring the braking with you. That means more propellant, more engines, more structure, more mass, and usually a more powerful launch. A Pluto orbiter would likely weigh far more than New Horizons, or leave Earth much more slowly, or both. A lander would demand even more. It would need power, thermal protection, landing hardware, and a way to survive in temperatures near minus 225 degrees Celsius. Pluto's thin nitrogen atmosphere offers little help for aerodynamic braking, so a landing mission would rely heavily on propulsion and precise guidance. And once you add those things, the whole mission changes. The spacecraft grows heavier, the launch becomes more difficult, the travel time often stretches, the price rises, the engineering grows more delicate. A flyby can afford to be light and fast. An orbiter or lander has to act more like a traveling outpost. It must arrive with enough remaining capability to do more than survive one pass. That is why crossing Pluto's distance is the easier half of the challenge. A flyby can touch the system once and leave with treasure. Staying asks for a deeper commitment. It asks for control at arrival, long-term power in faint sunlight, reliable communication across billions of kilometers, and hardware that can keep functioning in intense cold, with no rescue and no quick repair. Once that becomes clear, Pluto changes again. It stops feeling like a distant label at the edge of a classroom diagram and starts feeling like something harsher, a real destination, with real conditions, waiting to test whatever reaches it. And Pluto earns that feeling the moment you look at the place itself. By the time a spacecraft reaches Pluto, the problem is no longer just distance. The environment begins pushing back too. Almost every easy assumption we carry from missions closer to the Sun starts to weaken. The light is weak. The cold is extreme. Commands take hours to arrive. Even simple operations become slow, deliberate, and fragile. Start with temperature. Pluto's surface is usually around minus 230 degrees Celsius, or about minus 382 degrees Fahrenheit, though the exact number can shift depending on location, altitude, season, and whether sunlight is hitting nitrogen frost or darker ground. Some measurements from the New Horizons flyby in July 2015 suggested parts of the surface were a little warmer than others, but still brutally cold by any human standard. This is a world where nitrogen, the main gas in Earth's air, can freeze solid onto the surface. Methane can freeze there too. Water ice exists on Pluto, but at those temperatures it behaves less like soft ice in a freezer and more like bedrock. That cold changes everything about spacecraft design. Materials contract in extreme cold. Lubricants can thicken. Electronics have to be insulated and heated carefully. Any lander or orbiter working around Pluto would need reliable thermal control just to keep its instruments alive. On Mars, the cold is serious. On Pluto, the cold becomes one of the defining conditions of existence. Then there is the light. Earth receives about 1,361 watts of solar energy per square meter at the top of the atmosphere. Pluto receives only a tiny fraction of that. Because sunlight spreads out as it moves away from the sun, a world around 39 astronomical units out gets about 1/1,500th of the sunlight Earth receives on average. That means solar panels become much less attractive. A spacecraft near Earth can unfold panels and drink in sunlight almost freely. At Pluto, the same panels would produce far less power, unless you make them very large. That is one reason New Horizons did not rely on solar panels. Instead, it used a radioisotope thermoelectric generator, often shortened to RTG. That is a power source that turns heat from the slow decay of radioactive material into electricity. In New Horizons' case, the fuel was plutonium-238. That kind of system is heavy, expensive, and limited in power. But it works far from the sun, where sunlight becomes too weak to depend on comfortably. A future Pluto orbiter or lander would likely face the same decision. If you want dependable power out there, you usually need nuclear help. The sky would feel strange too. At Pluto, the sun is still much brighter than any star, but it looks small and sharp, more like an intense point of light than the broad, warm disk we know from Earth. Daylight exists, but it is thin. The overall feeling would be dim, distant, and severe. Beautiful, certainly, but operationally awkward. Cameras need careful exposure. Solar heating is weak. Thermal swings can be harsh. And then there is communication. When New Horizons flew past Pluto in 2015, the radio signal travel time between Earth and the spacecraft was about 4.5 hours one way. At Pluto's average distance, it is more like 5.5 hours one way. That means a simple back and forth exchange can take 9 to 11 hours. If engineers on Earth notice a problem and send a command, that command does not arrive in minutes. It arrives much later. If the spacecraft responds, the answer comes back later still. So real-time control disappears. There is no joystick, no live piloting, no quick correction from mission control. A spacecraft at Pluto has to do much more for itself. It must know how to point its antenna, protect its instruments, manage faults, and follow a timeline with very little immediate human help. That is manageable for a flyby probe built carefully enough. It becomes more demanding for an orbiter, and harder still for a lander working on the surface. All of this means Pluto is difficult in a deeper way than the trip alone suggests. It is cold enough to freeze familiar gases, dim enough to weaken ordinary solar power, slow enough in communication that Earth becomes a distant supervisor instead of an active pilot. And once the destination itself grows this dim and this slow, distance starts turning into something heavier than travel time alone. By the time a mission reaches Pluto, remoteness stops being a background fact and starts shaping the entire experience of exploration. At Mars, engineers can still think in terms of a long delay. At Pluto, the delay becomes part of the environment. Radio signals travel at the speed of light, which is as fast as anything in the universe can move, and even that is slow on Pluto scales. Depending on where Pluto and Earth are in their orbits, a radio message can take roughly 4.5 to 7 hours one way. Around the time of the New Horizons flyby on July the 14th, 2015, the one-way light time was about 4 hours and 25 minutes. At Pluto's average distance from the Sun, and with Earth positioned elsewhere on its own orbit, the delay can stretch beyond 5 hours, and in some geometries it goes farther still. That means a simple exchange can consume most of a day. If a spacecraft near Pluto sends a status report to Earth at noon spacecraft time, mission control may not receive it until late afternoon or evening. If engineers study the problem, make a decision, and send back a command, that answer may not arrive until the middle of the night, or even the next day. A round trip of information can take 9 to 14 hours, sometimes more. By then, the spacecraft has already moved on, the lighting conditions have changed, and the moment that caused the concern may be long gone. That changes the feel of the mission completely. There is no real-time piloting. No one on Earth is guiding a Pluto spacecraft with live hands. No one is looking through a camera feed and nudging the craft gently left or right. That style of control belongs to aircraft, drones, and science fiction. A Pluto mission lives by preloaded timelines, tested sequences, and patience. New Horizons is a good example of how strict that has to be. During the 2015 flyby, the spacecraft executed an encounter sequence that had been planned and rehearsed long before the closest approach. At the crucial moment, it rotated, pointed instruments, stored data, and protected itself largely on its own. Engineers on Earth could not watch events unfold and intervene in real time. They had to trust the spacecraft. The signal confirming that New Horizons had survived closest approach did not reach Earth until later that evening. For hours, the team had to wait in silence, knowing the spacecraft was either carrying out one of the most ambitious planetary flybys ever attempted or had already failed beyond immediate help. That is what Pluto does to mission control. It turns action into waiting. And waiting is not passive. It is built on preparation. Outer solar system missions survive on planning, autonomy, and patience. Autonomy means the spacecraft can make small decisions for itself. It can detect some faults, switch to backup systems, enter a safe mode, or follow a programmed sequence without fresh instructions from Earth. Safe mode is a kind of protective state, where the spacecraft stops non-essential activity and focuses on keeping itself alive and in communication. That can save a mission, but even then, Earth still has to wait hours just to learn what happened. Mistakes become heavier in that kind of environment. A bad command sent to a spacecraft near Earth can sometimes be corrected quickly. A bad command sent to Pluto may take hours to arrive, and the repair may take hours more. If the problem affects pointing, power, or data collection during a brief flyby, the lost opportunity may never return. Pluto is so far away that even small errors can become permanent. So the mission starts feeling isolated even when it is robotic. It becomes a lonely machine working in weak sunlight, carrying a small nuclear power source, following instructions written by people half a day away in signal time. Every image, every measurement, every health report has to cross billions of kilometers before anyone sees it. The spacecraft is still part of a human mission, but it operates with a strange kind of independence forced on it by distance. And once even a robotic mission begins to feel this isolated, the next question arrives almost automatically. If Pluto already feels lonely for a machine, what would that distance mean for actual human beings? A robotic mission can spend years in silence and darkness, Because a machine does not need comfort, oxygen, sleep, privacy, or hope. The moment you put people on the spacecraft, the question changes completely. A human mission to Pluto would no longer be only a problem of distance and speed. It would become a moving life support system that had to stay healthy, pressurized, powered, and psychologically stable for years. Every day of travel would have to keep human beings alive inside a sealed environment, far beyond any quick rescue, with almost no margin for major failure. Start with the simplest needs. A human crew needs breathable air, drinkable water, food, temperature control, waste removal, medical supplies, exercise equipment, sleeping space, and protection from radiation. None of those are optional. On Earth, these needs are handled by a whole planet. On a spacecraft, every one of them has to be packed, recycled, monitored, and repaired by the mission itself. Air sounds simple until you remember how quickly it becomes a closed-loop engineering problem. A crew exhales carbon dioxide and consumes oxygen every hour of every day. That means the spacecraft needs systems to scrub carbon dioxide from the cabin and replace oxygen safely. Water becomes equally demanding. People need it for drinking, food preparation, hygiene, and cooling systems. Over a mission lasting years, carrying every drop from Earth would be brutally expensive in mass. So the spacecraft would need recycling systems, the kind already used in orbit, but pushed much farther and for much longer. Food becomes another heavy reality. A person can survive for weeks without food, but not for the many years a Pluto mission would require. Even dried food has mass. Packaging has mass. Storage has mass. If the mission tried to carry full food supplies for a long, crewed Pluto journey, the mass would grow quickly. That is before you even consider menu variety, vitamins, spoilage, or crew morale. Then there is waste. Human beings produce carbon dioxide, urine, solid waste, heat, and moisture constantly. A crewed Pluto mission would need to process all of it cleanly and reliably for years. A failed toilet on Earth is a terrible inconvenience. A failed waste system far beyond Mars becomes a mission-threatening event. The medical side is just as serious. A human crew might need antibiotics, pain medication, surgical tools, emergency supplies, and some way to diagnose illness. A broken bone, a kidney stone, appendicitis, severe infection, depression, or vision problems all become more dangerous when the nearest hospital is many years away. Radiation adds another layer. Once a crew leaves Earth's magnetic field, it loses one of the planet's most useful protections. Deep space contains energetic particles from the Sun and from more distant cosmic events. Over a short mission, the risk is serious but limited. Over years, it accumulates. A Pluto crew would likely spend far longer in deep space than any crew in human history. That means more shielding, more storm protection, and more mass. And Pluto is much farther away than Mars. A crewed Mars mission is already considered difficult, partly because the one-way trip might take roughly 6 to 9 months with current mission concepts. Pluto, even using the New Horizons benchmark as a rough emotional reference, sits on a timescale of many years, not months. And a human spacecraft would almost certainly be heavier than New Horizons, which means the trip could stretch longer unless enormous launch energy is added. That extra mass comes from survival itself. Crew cabins add mass. Water tanks add mass. Food stores add mass. Radiation shielding adds mass. Backup parts add mass. Redundancy, which means carrying spare systems in case one fails, adds mass too. And every kilogram added to keep the crew alive loops directly back into the speed problem. A heavier spacecraft is harder to accelerate. Harder to accelerate means slower travel, or a bigger rocket or more propellant, or some painful combination of all three. So human presence changes the meaning of the journey. A robotic Pluto mission is a long technical crossing. A human Pluto mission becomes a years-long attempt to protect fragile bodies and fragile moods inside a machine that must behave like a tiny artificial world. And once people are inside that world, the years to Pluto stop feeling like mission numbers. They start feeling like something else entirely. A real slice of a life. And that is where the number stops behaving like a mission number. For a crew, the years to Pluto would be years taken from a human life and spent inside a machine. New Horizons took about 9.5 years to reach Pluto, and New Horizons was an uncrewed probe weighing less than 500 kilograms at launch. A human spacecraft would be far heavier. It would need pressure hulls, sleeping space, food, water, medical supplies, exercise equipment, radiation shielding, waste systems, spare parts, and backup systems for almost everything important. That extra mass would make high speed harder to buy. So even a relatively fast human Pluto mission would likely mean many years outbound alone, and possibly longer than the New Horizons crossing, unless launch power improved dramatically. That changes the emotional meaning of the trip. A mission lasting several years is not just long. It cuts through normal life. If a crew member launched at age 30, and the outbound journey alone consumed something like 8, 10, or 12 years, they would arrive in a different phase of adulthood than the one they left behind. If the mission included time at Pluto and some kind of return, the total span could occupy a decade or more, perhaps much more. That is enough time for children on Earth to grow from elementary school into college age. It is enough time for parents to age noticeably, for careers to disappear, for whole eras of public life to change. And all of that would be happening while the crew was still in transit. We already know from Earth-based analog missions that confinement changes people, even over much shorter periods. The Mars 500 study in Moscow sealed 6 men inside a mock spacecraft for 520 days, from 2010 to 2011, to imitate a Mars mission. That is less than a year and a half. Even in that controlled setting, researchers tracked disrupted sleep, mood changes, social strain, and signs of monotony. At Concordia Station in Antarctica, where winter crews live in extreme isolation and darkness, doctors and psychologists have studied stress, low mood, sleep disruption, and what some call the winter over syndrome, a cluster of fatigue, irritability, and mental slowing that can develop in long cut-off missions. Submarine patrols show similar patterns: small groups, sealed environments, repeating routines, no easy exit. Those missions last months. Pluto would ask for years, and Pluto would offer almost none of the emotional compensation that human beings usually use to get through hard stretches of time. There would be no changing landscapes outside the window in the ordinary sense. No weather fronts rolling in, no open air, no cities, no trees, no new voices dropping by. The ship would become the whole world, the same walls, the same meals, the same few faces, the same mechanical sounds repeated day after day. That kind of repetition matters. Human beings are good at enduring difficulty when the difficulty has rhythm and variation. A sailor still sees changing seas. A polar researcher still steps into a real environment. An astronaut in low Earth orbit sees Earth every 90 minutes, blue and bright beneath the station. A Pluto crew would spend long stretches heading toward a place so remote and dim that even the destination would remain abstract for much of the voyage. And the destination itself would not feel emotionally familiar. Mars has deserts, dust, and a day just over 24 hours long. The moon hangs visibly above Earth and has been part of human culture for thousands of years. Pluto belongs to almost no inherited human imagination. It is a small, cold world in a region most people have never truly pictured in their minds. A crew would be giving years of life to a place that has almost no natural emotional anchor in ordinary experience. That is why the cost begins to feel so large. The crew would not just be traveling to Pluto. They would be aging toward Pluto, spending birthdays in transit, watching muscles need constant maintenance, watching friendships either deepen or fray, watching the years themselves become part of the payload. And once the human cost becomes visible like that, Pluto starts to feel larger than a destination. It starts to feel more like a boundary. By the time we reach Pluto in this story, something important has changed inside the menesque of the journey. Mars still feels connected to us. It has seasons. It has polar caps. It has dust storms, canyons, volcanoes, and a day that lasts 24 hours and 39 minutes, close enough to Earth's rhythm to feel familiar. Even when Mars is far away, it still belongs to the inner human imagination. It looks like a place where boots could leave prints, where habitats could stand under a salmon-colored sky, where people might one day build routines. Pluto carries a different feeling entirely. Part of that difference comes from distance. Mars can come within tens of millions of kilometers of Earth during favorable oppositions. Pluto sits billions of kilometers away. Part of it comes from temperature. Mars can reach room-like temperatures for short periods in sunlit places near the equator. Pluto lives around -230 degrees Celsius. Part of it comes from light. Mars still receives workable sunlight for solar power. Pluto receives about 1/1500th of the sunlight Earth gets. But part of it also comes from where Pluto belongs in the map of the solar system. Pluto sits in the Kuiper belt. The Kuiper belt is a broad region beyond Neptune, filled with icy bodies left over from the solar system's formation about 4.5 billion years ago. It begins around 30 astronomical units from the Sun, near Neptune's orbit, and stretches outward for many billions of kilometers. Pluto is one of the largest known objects there, along with bodies like Eris, Haumea, and Makemake. This is a population of frozen remnants, many smaller than Pluto, many darker, many stranger, all circling in a region where the Sun still rules, but feels far less personal. That matters because Pluto stops feeling like the last planet and starts feeling like the first member of another realm. The inner planets belong to one story. Mercury, Venus, Earth, and Mars form the compact, sunlit, rocky beginning of the solar system. Jupiter and Saturn enlarge the scale dramatically, but they still sit within a region that human beings have mentally explored for centuries through telescopes, spacecraft, and myth. Uranus and Neptune already begin to thin out the familiar world. Pluto carries that thinning much farther. By Pluto, you are no longer visiting a distant variation of the planetary neighborhood. You are stepping into a zone of icy relics, long orbital periods, and weak sunlight, where ordinary human intuition starts to fail. Even the sun changes character out there. On Earth, the sun defines the day. It warms the skin, brightens the clouds, grows crops, and sets the rhythm of ordinary life. At Pluto, it remains physically central. Pluto still orbits it. Pluto's seasons still depend on it. Pluto's frosts and hazes respond to it. But in an everyday sense, the sun no longer feels close. It appears as an intense point of light, rather than a broad, dominating disk. It still casts light, but thinly. It still matters, but from a distance so great that warmth no longer feels like part of the relationship. That psychological shift is one of the deepest parts of the Pluto journey. Up to a certain point, the solar system still feels like a large home. By Pluto, it begins to feel like a frontier. The words stay the same. Planet, orbit, moon, sun, spacecraft. But the meanings start to stretch. Travel stops feeling like a long trip and starts feeling like a crossing into a colder layer of reality. That is why Pluto matters so much in this story. It is small. It is distant. It is not the most massive world, or the hottest, or the most energetic. But it is one of the first places where the human mind fully loses its everyday grip on scale and familiarity. Reaching Pluto begins to feel less like checking another world off a list, and more like placing a hand on the edge of something larger. And once Pluto becomes that kind of place, the journey toward it starts to look different too. It starts to look less like a mission to one dwarf planet, and more like contact with a threshold. That is why a mission to Pluto begins to mean more than Pluto alone. Pluto matters partly because it is a world with mountains, glaciers, haze, and moons. But it also matters because it stands near the doorway to a much larger region. When New Horizons reached Pluto in July 2015, it was doing more than visiting one dwarf planet. It was crossing into the first clearly explored stretch of the Kuiper belt, the broad outer zone beyond Neptune, where countless icy bodies orbit the Sun. Pluto is one of the largest known objects in that region, with a diameter of about 2,377 kilometers. That makes it smaller than Earth's moon, which is about 3,474 kilometers across, but still large enough to hold a complex surface and a thin atmosphere. Yet Pluto is far from alone. Eris, another dwarf planet discovered in 2005, is similar in size and slightly more massive. Haumea is shaped oddly because it spins so fast. Makemake is another bright, icy dwarf world. Beyond those better-known names lie thousands of smaller objects, and likely many more still too faint to detect easily. This outer region is full of leftovers. The Kuiper belt is thought to contain material left from the solar system's formation around 4.5 billion years ago. Closer to the Sun, intense heat and repeated gravitational reshaping helped organize the planets we know best. Farther out, beyond Neptune, many icy bodies remained as fragments of that early construction zone. They are made largely of frozen substances like water ice, methane ice, nitrogen ice, and other volatile compounds, which is a scientific word for materials that evaporate or sublimate easily when warmed. Near Pluto, these materials can remain frozen for billions of years. That gives the Kuiper belt a different feeling from the planetary system most people picture first. The classical planets form a kind of backbone in the schoolbook solar system. Mercury through Neptune feels like a sequence. Pluto changes the texture of that sequence. Once you reach it, the solar system stops feeling like a neat list of major worlds and starts feeling more like a wide field of ancient debris, scattered bodies, and slow, cold motion. That is one reason New Horizons kept going after Pluto. After the Pluto flyby, the spacecraft did not turn back. It continued outward into the Kuiper belt and later reached another object, Arrokoth, on January 1st, 2019. Arrokoth is much smaller than Pluto, about 36 kilometers long, and it looks like two lobes gently joined together, almost like a snowman flattened into space. That shape gave scientists a rare look at how small early bodies may have merged in the young solar system. In other words, the mission used Pluto as a gateway. Pluto was the great landmark, but the region beyond it still had more to show. That changes the meaning of the trip. A Pluto mission is not only a long journey to one distant dwarf planet. It is also humanity's first direct encounter with an outer solar system landscape that lies beyond the last major planet. It is the beginning of a different map. A map of icy relics, dim sunlight, broad separations, and orbital periods so long that human history occupies only a small fraction of a single circuit. Pluto stands at the threshold because it is large enough to be vivid and distant enough to reveal the region behind it. Before Pluto, the outer solar system still feels like a chain of named planets. After Pluto, it opens into something wider and less tidy. A mission that reaches Pluto is already touching that change. It is already brushing against a part of the solar system that feels older, quieter, and less domesticated by familiar categories. And once Pluto becomes that kind of threshold, another realization follows almost automatically. Even after all those years of travel, even after all that distance, the solar system is still not over. That is the next great surprise. Pluto feels like the edge only until you look past it. For generations, Pluto carried that emotional role in popular astronomy. It was the last named world in the old classroom lineup, the small, cold outpost at the end of the planetary road. But once spacecraft and better telescopes forced us to look more carefully, the picture widened. Pluto turned out to be remote, yes, but still very much inside a larger structure that extends far beyond it. The first layer beyond Pluto is the rest of the Kuiper belt. The Kuiper belt begins beyond Neptune, around 30 astronomical units from the Sun, and continues outward for many billions of kilometers. Pluto's average distance is about 39 astronomical units, which places it inside that region, not beyond it. And the Kuiper belt does not stop neatly at Pluto's orbit. It continues outward with many other objects, some in relatively stable orbits, others pulled into stranger paths by the gravity of Neptune and the long history of the solar system. Some of those paths are highly stretched. Some are tilted. Some carry objects much farther out than Pluto. Astronomers sometimes call part of this more chaotic population the scattered disk, a region of bodies whose orbits were likely disturbed long ago by Neptune's gravity. One well-known example is Eris, discovered in 2005, which can travel out to roughly 97 astronomical units from the Sun at its most distant point. Another is Sedna, discovered in 2003, whose orbit is far stranger still. Sedna comes no closer than about 76 astronomical units and goes out to around 900 astronomical units at its farthest. A single Sedna year lasts about 11,400 Earth years. Those numbers change the feeling of Pluto immediately. If Sedna can wander hundreds of astronomical units out, then Pluto is no longer the farthest meaningful member of the Sun's family. It becomes one of the first major landmarks in a much wider outer zone. And beyond even those icy bodies lies something larger still: the Oort cloud. The Oort cloud has never been seen directly, which is why astronomers call it hypothesized, meaning strongly inferred rather than photographed outright. The idea was proposed in 1950 by Dutch astronomer Jan Oort to explain the arrival of long-period comets, the ones that take thousands or even millions of years to swing around the Sun. The thought is that the Sun is surrounded by an immense spherical cloud of icy objects left over from the early solar system, loosely bound by gravity and extending far into interstellar space. The inner part of that cloud may begin somewhere around 2,000 astronomical units from the Sun. The outer parts may stretch to 50,000 astronomical units, perhaps even 100,000 astronomical units in some models. Since 1 astronomical unit is about 150 million kilometers, those are staggering distances. At 100,000 astronomical units, you are talking about a region roughly 1.5 times 10 to the 13th kilometers out, on the order of 1.5 light years from the Sun. That is still closer than Alpha Centauri, but it is vastly beyond Pluto. In that wider context, Pluto changes size emotionally. It is still distant enough to demand years of travel, still cold enough to freeze nitrogen, still remote enough that sunlight arrives weakly and radio commands crawl outward for hours. But it is also still deep inside the Sun's broader gravitational reach. The Sun's influence does not end at Pluto, or at Neptune, or even at the Kuiper belt. It fades gradually across a domain so large that Pluto begins to feel like an early outer marker rather than a final border. That is what makes the scale of the solar system so unsettling and so beautiful at the same time. You can travel for nearly a decade to reach Pluto, and still remain far inside the larger territory shaped by the Sun. You can reach a world that feels like the end of everything familiar, and discover that it stands only near the beginning of the far outer dark. And once Pluto becomes both distant and still somehow interior, the journey to it starts to feel impressive and small at the same time. That is the humbling turn waiting inside the whole journey. A mission to Pluto would be a genuine human achievement. It would take years of planning, years of flight, careful launch timing, a powerful rocket, a well-balanced spacecraft, and an enormous amount of trust in machines operating far from home. It would also reveal something uncomfortable. Even after all that effort, we would still be traveling inside our own solar system. New Horizons makes that clear better than any abstract comparison can. The spacecraft launched on January 19, 2006, from Cape Canaveral and reached Pluto on July 14, 2015. The mission took about 9.5 years to cross the distance. It needed one of the fastest planetary launches ever achieved, a carefully chosen route, and a gravity assist from Jupiter in February 2007 to cut years from the flight time. It arrived moving fast enough to race through the Pluto system in a brief burst of observation, capturing mountains, ice plains, haze, and moons that humanity had never seen clearly before. That is a remarkable thing for our species to have done. It means we can build a machine on Earth, send it across billions of kilometers, and guide it to a precise target in the dim outer solar system. That deserves its full weight. A Pluto mission is hard. It asks for engineering discipline, patience, money, timing, and years of collective attention. And still, Pluto remains local in the larger map. Pluto's average distance from the Sun is about 39 astronomical units. The Kuiper belt extends beyond it. The inner edge of the Oort cloud may begin around 2,000 astronomical units. The nearest star, Proxima Centauri, is about 4.24 light-years away, roughly 268,000 astronomical units. So a mission to Pluto, impressive as it is, does not even begin to approach interstellar travel. It stays deep inside the Sun's extended domain. That is the deeper lesson hidden inside the success. Human beings often speak about space as though it were one place, one smooth category. But the journey to Pluto shows how layered it really is. Low Earth orbit is one world. The Moon is another. Mars is another. Jupiter and Saturn widen the scale again. Pluto reveals a colder and more distant layer still. And beyond Pluto, the solar system continues outward for distances that make even a decade-long mission feel modest. That is why the trip feels both triumphant and limited at the same time. We can reach Pluto. That matters. We cannot reach Pluto casually. That matters just as much. A mission there already demands the kind of effort people once reserved for crossing oceans, then continents, then worlds. And yet the destination still belongs to our own stellar backyard. That tells us something serious about our current place in cosmic history. We are capable of reaching outward. We are still doing it slowly. Every major gain costs us. Every success arrives inside a scale that remains far larger than our instincts expect. In that sense, Pluto becomes a measuring line. It shows what our best machines can do. It also shows how much farther reality extends beyond our best machines. A civilization that needs nearly 10 years to send a small probe to Pluto is a civilization still learning how expensive distance really is. A crewed Pluto mission with life support, shielding, food, water, and return options would expose that cost even more harshly. So the trip is impressive partly because it barely solves the bigger problem. It gets us to one cold dwarf world near the threshold of the outer solar system. It does not make space easy. It does not make the Sun's farthest territory feel small. It does not shrink the darkness waiting beyond. And that contradiction prepares the final thought almost by itself. Pluto is close enough for us to attempt, and far enough to show us exactly what space demands. So after all of this, Pluto settles into view as two things at once. It is a promise, and it is a warning. It is a promise because we have already reached it. On January 19, 2006, a spacecraft left Earth from Cape Canaveral. On July 14, 2015, that same spacecraft, New Horizons, arrived at Pluto after a journey of about 9.5 years. It crossed billions of kilometers, used a gravity assist from Jupiter in 2007, survived the cold and darkness of the outer solar system, and gave humanity its first clear look at a world that had lived for generations as little more than a shifting blur of light. That matters. It means Pluto is not fantasy. It is not a symbolic edge drawn on an old classroom poster. It is a real place that human-built hardware can reach. Its surface has mountains of water ice several kilometers high. Its bright basin, Sputnik Planitia, is made largely of frozen nitrogen. Its atmosphere is thin and layered with haze. It has moons. It has seasons. It has weather on a rhythm so slow that a single Pluto year lasts 248 Earth years. A place like that can sound almost mythic until a spacecraft actually arrives and turns it into geography. That is the hopeful side of Pluto. It tells us that human reach is real, that our machines can leave one world and touch another in the deep cold beyond Neptune, that patience, mathematics, and engineering can still pull something astonishing out of the dark. But Pluto is also a warning, because even this reachable place came at a serious cost. It took one of the fastest planetary launches ever achieved. It required a carefully timed path through the solar system. It depended on Jupiter being in the right place to help. It gave us a flyby rather than an orbiter, because slowing down would have demanded a heavier, harder, more expensive mission. Radio signals took hours to cross the distance. The sunlight was so weak that solar power became far less practical. The spacecraft had to carry a nuclear power source and survive in temperatures around minus 230 degrees Celsius. And after all of that, Pluto was still only Pluto, still inside our own solar system, still within the sun's gravitational domain, still far short of the stars. That is the sobering side of the story. If a small robotic mission needs nearly a decade to reach Pluto, then space reveals its price much earlier than human intuition wants to admit. The cost begins long before interstellar travel. It begins here, within the sun's own family, at a cold dwarf world that many people once treated as the last easy name on a list. Pluto shows us that distance does not wait until the stars to become difficult. Distance becomes difficult within the solar system itself. It becomes a test of launch energy, timing, mass, patience, communication delay, thermal control, and endurance. It becomes a test of whether a mission can still function when the sun is only a hard, bright point in a dim sky. It becomes a test of whether people on Earth can plan carefully enough to support a spacecraft they cannot quickly help. That is why Pluto feels so important. It is close enough to attempt, and far enough to humble us. Close enough to invite ambition, and far enough to expose how expensive ambition becomes once the numbers turn real. So the question we began with, if we left in 2026, how long would it take to reach Pluto, ends up opening something larger than a travel estimate. It becomes a quieter question about scale, about patience, and about what kind of species we are trying to become. Because once even Pluto demands this much from us, the deeper question is already waiting beyond it. If this is what it takes to reach one small world near the threshold of the outer solar system, then how far can human travel really go?